In the present lecture, we shall discuss the Bhattacharya system of lower bounds of the variance of an unbiased estimator. It is a generalization of the Cramer-Rao lower bound of the variance of an unbiased estimator. First, we shall discuss the regularity conditions under which one can define the Bhattacharya system of lower bounds. Next, we shall prove the main theorem along with a detailed discussion on the case of equality. Next, we shall prove a very important result that will show the increasing behavior of the sequence of lower bounds. In this lecture, we shall discuss a generalization of Cramer-Rao lower bound which is known as Bhattacharya system of lower bounds. Let us consider a family of distributions script f theta equals to set of all f theta x such that theta belongs to script theta, which satisfies the following regularity conditions. Number 1, script theta is an open interval of the real line. Number 2, the support script x which is equals to set of all x for which f theta x greater than 0 does not depend on theta. Number 3, for some integer k del to the power I by del theta to the power I f theta x exists for all x and for all theta for all I from 1 to up to k. Number 4, for any statistic hx with expectation of hx is finite for all theta, del to the power I by del theta to the power I expectation of hx is equals to del to the power I by del theta to the power I integral hx f theta x dx, which is equals to integral hx del to the power I by del theta to the power I f theta x dx for all theta and for all I from 1 to k. That is, we can interchange the differentiation up to the order k and the integration sign. The fifth condition is the matrix capital Vk whose elements are Vij, where Vij equals to expectation del to the power I by del theta to the power I log f theta x into del to the power j by del theta to the power j log f theta x, where theta belongs to script theta, exists for all theta and V is positive definite. Now we are going to the main theorem. Let the family of distributions script f theta satisfies the Bhattacharya regularity conditions and g theta be a real valued function of theta such that g theta is k times differentiable for some integer k. Let capital T be an unbiased estimator of g theta such that variance of t is finite for all theta. Then variance of t is greater than equals to vector g prime vk inverse into vector g for all theta, where vector g is equals to g upper 1 theta, g upper 2 theta up to g upper k theta, where g upper I theta is equals to the partial derivative of g theta with respect to theta of order I. Note that for k equals to 1, the Bhattacharya lower bound and the regularity conditions reduces to Cramer-Rao lower bound and the corresponding regularity conditions. Now we prove the above theorem. Let us define Si, which is a function of theta and x, which is equals to 1 by f theta x into del to the power I by del theta to the power I into f theta x. Hence, expectation of SI is equals to integral 1 by f theta x into del to the power I by del theta to the power I f theta x into f theta x dx, which is equals to integral del to the power I by del theta to the power I into f theta x dx. Interchanging the differentiation sign and the integral sign, we get del to the power I by del theta to the power I integral f theta x dx, which is equals to 0 for all I. Therefore, variance of SI is equals to small v II, and the covariance between SI and Sj is equals to small vij. Now, covariance between Si and T is equals to expectation Si into T, which is equals to integral Tx into 1 by f theta x into del to the power I by del theta to the power I f theta x into f theta x dx, which is equals to del to the power I by del theta to the power I integral Tx f theta x dx after interchanging the integral and the differentiation sign, which is equals to del to the power I by del theta to the power I g theta, that is g upper I theta. Let capital sigma be the dispersion matrix of T, S1, S2 up to Sk, which is equals to, in the diagonal elements are the variance of T and the variance of S1, S2 up to Sk, and all the covariances term in the off diagonals. And this is looked as, in the first row there is variance of T with g upper 1 theta up to g upper k theta, and in the first column there is g upper 1 theta up to g upper k theta, and in the remaining part there is a matrix Vk. Since sigma is PD, we get determinant of sigma greater than equals to 0. Now, determinant of sigma is equals to determinant Vk into variance of T minus g prime Vk inverse into g, which is greater than equals to 0. Thus, we get variance of T is greater than equals to g prime Vk inverse into g. Now we consider the case of equality. The equality sign holds if determinant of sigma equals to 0, that is, rank of sigma is less than k plus 1, and hence rank of sigma is equals to k, since sigma contains v which is non-singular. Hence, there exists a non-zero vector L such that T minus g theta equals to L prime into S vector, where S vector is equals to S1, S2 up to Sk, which implies T minus g theta equals to g prime into Vk inverse into S vector with probability 1. To prove this, let us note that variance of L prime S minus g prime Vk inverse S is equals to variance of T minus g theta minus g prime Vk inverse S, which is equals to variance of T plus g prime into Vk inverse into dispersion of S minus 2 into covariance between T and g prime Vk inverse S, which is equals to g prime into Vk inverse into g plus g prime into Vk inverse into g minus twice g prime into Vk inverse into g, which is equals to 0. Hence, L curl prime S minus g prime Vk inverse S is equals to expectation of L curl prime S minus g prime Vk inverse S, which is equals to 0 with probability 1. Thus, we get T minus g theta equals to L prime S, which is equals to g prime Vk inverse S with probability 1. Now, we consider a very important result relating to the Bhattacharya system of lower bounds. Suppose the nth lower bound be denoted by capital delta n, which is equals to gn prime into vn inverse into gn, where gn prime is a row vector whose elements are g upper 1 theta, g upper 2 theta up to g upper n theta. The sequence of lower bounds delta n is a non-decreasing sequence, that is delta n plus 1 is greater than equals to delta n. Observe that delta 1 is the Cramer-Rao lower bound. To prove the result, note that delta n plus 1 is equals to g n plus 1 prime into v n plus 1 inverse into g n plus 1, where g n plus 1 prime is a vector with elements g upper 1 theta, g upper 2 theta up to g upper n plus 1 theta. The vector g n plus 1 prime and the matrix v n plus 1 can be partitioned as follows: g n plus 1 prime equals to g n prime partition g upper n plus 1 bracket theta, and v n plus 1 can be partitioned as Vn, a matrix, and the matrix Vn plus 1 is partitioned in the form Vn u n plus 1 u n plus 1 prime and small v n plus 1 n plus 1. Now for any non-singular matrix C, we can write delta n plus 1 equals to g n plus 1 prime into C prime inverse into v n plus 1 inverse into C prime inverse into C prime into g n plus 1, which can be written as C into g n plus 1 prime into C into v n plus 1 into C prime inverse into C g n plus 1. Now if we choose the matrix C in the form I n 0 minus u n plus 1 prime into v n and 1, then we have C into g n plus 1 is a vector with elements g n and g n plus 1 minus u n plus 1 prime v n into g n. Thus we get C into v n plus 1 into C prime in the form of a partition matrix v n 0 0 e n plus 1 comma n plus 1, where E n plus 1 n plus 1 is equals to v n plus 1 n plus 1 minus u n plus 1 prime into v n into u n plus 1. Since v n plus 1 is PD, v n is PD and E n plus 1 n plus 1 greater than 0, we have C v n plus 1 C prime whole inverse is equals to v n inverse 0 0 1 by E n plus 1 n plus 1. So we finally get delta n plus 1 equals to g n prime v n inverse into g n plus a non-negative quantity. Therefore, delta n plus 1 is greater than equals to delta n. The implication of the result is that if there is no unbiased estimator of g theta which attains the nth lower bound delta n, then a sharper lower bound delta n plus 1 can be obtained and looked at. If an unbiased estimator satisfies the nth lower bound delta n, then no further improvement can be made and hence delta n plus 1 is equals to delta n. However, delta n equals to delta n plus 1 does not imply that there exists an unbiased estimator of g theta which attains the nth lower bound. It is clear from the following example. Let x1, x2 up to xn be a random sample from normal population with parameter theta and 1. In the last module, we have seen that there does not exist an unbiased estimator of theta square which attains delta 1, that is the Cramer-Rao lower bound. Now we want to find an unbiased estimator of theta square which attains the Bhattacharya lower bound delta 2. The joint PDF of x1, x2 up to xn is given by f theta x vector is equals to 1 by root 2 pi whole to the power n into e to the power minus half into summation over I from 1 to n xi minus theta whole square, where minus infinity less than xi less than infinity for all I. Hence, S1 is equals to 1 by f theta x vector into del by del theta f theta x, which is equals to 1 by f theta x into f theta x into summation over I from 1 to n xi minus theta, which in turn equals to n into x bar minus theta, where x bar is equals to 1 by n into summation over I from 1 to n xi. Now, S2 is equals to 1 by f theta x into del square by del theta square into f theta x. Now, S2 is equals to 1 by f theta x into del square by del theta square f theta x, which is equals to 1 by f theta x into del by del theta f theta x into summation over I from 1 to n xi minus theta. After simplification, we get S2 equals to n square into x bar minus theta whole square minus n. By definition, we know expectation of S1 equals to 0, expectation of S2 equals to 0. Now, expectation S1 square is equals to n into x bar minus theta whole square, which is equals to n square into 1 by n, because x bar follows normal with mean theta and variance n, and thus we get expectation of S1 square is equals to n, and expectation S2 square is equals to expectation n to the power 4 into x bar minus theta whole square plus n square minus 2n cube into x bar minus theta whole square, which is equals to n to the power 4 into 3 into 1 by n square plus n square minus 2n cube into 1 by n, which is equals to 2n square. Now, expectation S1 into S2 is equals to n square into expectation x bar minus theta whole cube minus n square expectation x bar minus theta, which is equals to 0, because the distribution of x bar is symmetric about theta. Therefore, we get V2 is a 2 cross 2 matrix whose elements are n, 0, 0 and 2n square. Since the parameter of interest under consideration is g theta equal to theta square, we have g prime vector is equals to 2 theta comma 2. Therefore, the V2 in the Bhattacharya system of lower bound for theta square is given by delta 2 equals to g prime V2 inverse g, which is equals to 4 by n into theta square plus 1 by 2n, which is equals to 4 theta square by n plus 2 by n square. The unbiased estimator of theta square, which attains the Bhattacharya lower bound of order 2, is given by g prime V2 inverse into s, which is equals to, after some algebraic simplification, this is equals to x bar square minus 1 by n minus theta square. After some algebraic simplifications, we get x bar square minus 1 by n. Therefore, capital T equals to x bar square minus 1 by n is the unbiased estimator of theta square, which attains the Bhattacharya lower bound of order 2. In the present lecture, we have seen that the Bhattacharya system of lower bounds is a generalization of the Cramer-Rao lower bounds, in the sense that when the variance of the UM-VUE does not attain the Cramer-Rao lower bound, it may attain the Bhattacharya lower bound of the higher order. For example, we have seen that in sampling from normal theta, 1 population, the UMVUV of theta square does not attain the Cramer-Rao lower bound, but it attains the Bhattacharya lower bound of order 2.